well, I made a copy of this, and then, and then like you're calling into this guy. At some point in the parent, you made another call, and then it sort of expanded to the next level, and then the next level gonna expand again to that, and then it's like something inside of that frame has expanded to the next one. It's like that.
Okay, that's a good visual. I like that.
All right. So last time we talked about how to traverse all the nodes in the tree, and we came up with this job queue, aka the to-do list approach. Um, and and then today, and then I guess the next challenge was how do we print every element in the tree in order?
Yeah.
But before we get into that, I'll just confess that this job queue based way of doing it is not the most common way.
Oh.
Yeah, it's actually like if you Google for how to traverse a binary tree, you will not find, it'll be harder to find this way.
Interesting.
Yes. So that's not to say it's not a good way, but I like this way myself. But I think it's not as well suited for the second challenge, um,
I see.
which is to print everything in order. So before we talk about how to do number 2, I want to also show you how to do it the more common way.
Okay.
Without the job queue thing. And that way you actually alluded to it last time, which is you said something like it's almost like I need another tree structure while traversing it that maps onto this tree structure.
Yeah.
Um, and that actually matches how things are done in the second way. So
Okay.
what's the second way? If I say the word recursion, does that ring a bell?
Yes. Yeah.
Okay. So can you imagine a recursive function that can traverse every element in this tree?
Yeah. So let's think.
So I'm gonna write, yeah, recursive traversal. I'll get recursive tree traversal. So that's our method number 2 for traversing a tree. Like, what would that look like? And I don't know if you want to. I'll just let you think. Yeah, I'll just let you
Okay.
think.
So I'll try to think out loud here so we can dialogue. So we're going to start, I would assume, I think it's pretty good assumption. We're going to start at the root of the tree, and then we're going to perform some series of actions that can be called. So it's going to be, there's going to be a condition at which we know to break out of the recursion. We have to set that condition.
Yeah,
And then we're
yeah,
going to,
good.
then we're
So
going to,
we'll call it the terminating condition,
okay.
and we'll
And
figure out what that is
I
in the.
think that might be a node with 2 null children, but no, that can't be right because we can get to the bottom and then we still have to. Okay, never mind, scratch that. I'm going to keep going with the high level. Okay, so we have to figure out our terminating condition, and then we want to determine what series of steps, break the series of steps that we have to take into like the smallest repeating sequence that can be called again on the subtree until the terminating conditions met. So we want like, okay, so we want, I think we want to make, we're going to have to store some things. And I don't know exactly what all we're going to have to store. Probably what I'm initially thinking might be overkill, but I think we're going to have to store with our current node and so we're still trying to print. Okay, we're trying to print every element, but in order. So basically like that graphic, that visual that we've done where we're moving the line from left to right.
For now, don't worry about the in order aspect just yet.
Okay.
Just get to every node in the tree, and then
Okay.
we'll deal with that later.
Gotcha. Okay. So right now we're just getting to all the nodes. We're printing every element. Okay. So question I'm now grappling with is, do we go completely down one side of the tree and then back up, or do we work our way down both sides simultaneously? But how do we work our way down both sides simultaneously? That's kind of what we did in the method last week, where we pushed them and then popped them off the queue.
We're not doing it simultaneously. It's not like we're starting two processes in parallel.
Okay.
We're still doing things in a specific order. And I guess when we did the queue method, the order in which the names are printed, that's the order in which we reach all the nodes, right? Kind of.
Yes.
Yeah, like Jenny, Jeff, John, and then so it's like we did level 1, and then we did level 2, and then we did all the ones in level 3.
Yeah.
That's fine. Like if we can get the recursive traversal to do that, that's fine. Or not. Or I just care about getting to every node for now.
Okay. So the thing that we're going to have is the reference to the parent node. So we need to know what our current node is and what its parent was, I think.
Okay. So like variables, current, and parent, let's say.
Yeah. And then also we're going to need to know.
So also like I'm gonna write out what calling this function might look like. Maybe we'll call it traverse print or something, and then we pass it the root node. So maybe traverse print takes a node of some sort, and because it's a recursive function, at some point it'll call itself.
Exactly.
Yeah.
Okay, so it's going to take in the parent node.
Oh, so we said put in the parent as well. So we might pass that in as a parameter. So initially, we'll pass in null as the parent, let's say.
Okay, I like that. That makes sense. Okay, so initially, we have traverse print with passing in Jenny and null. And then I think the next thing would be to print that value, print the current value.
Okay, just go ahead and print it. Okay.
Yeah. Print node. Then
let me move our
So we move our pointer to one of our children.
Oh, move our pointer to I see what you're saying. Like
start traversing
the tree. Let me move this stuff. Let me try moving this. Is it shift? Yes, it's shift. Okay. So when you say move the pointer, so I guess like this frame thing, I think it's important again because this
Yes.
frame thing is very well matched to what recursion does. Because when you're calling a function, actually, in fact, um, there is a frame. uh, so calling this like this, so like when you make a function call, we actually add a new thing called the frame on the programming stack. And that frame is responsible for storing all the local variables inside your function. So which means like if we say this is a rectangle is a representation of a frame, then we're saying, hey, inside this frame, we're gonna store the variables. And the current is gonna be Jenny. And then we're gonna have a parent, which is null. So like something like that. Oh,
Yeah.
I probably shouldn't have done that.
I can imagine them being there.
Okay. So something like this, and then and we talked about moving the frame down the tree.
Yes.
While that's a valid way of looking at it, in reality, when you move the frame down the tree, it's the parent frame has made a inner function call, right? Which
Okay.
and when you make the so that would happen when you how do we get rid of these boxes, by the way? Okay, maybe that's it. Okay, so okay, go away boxes. All right, so at some point in your function, you're gonna say something like, "Hey, traverse print node dot left," right?
Correct.
And this is a recursive call, which mean, but when you call this function, the parent frame doesn't go away, right?
Right.
The parent, you still remember everything in the parent frame. You just increased you call this function sort of like nested inside the parent frame.
Okay.
So, so I guess that's so you should keep that in mind. Like when you move it, it's more like, well, I made a copy of this, and then, and then like you're calling into this guy. But this is like like you opened it up from the parent. Like at some point in the parent, you made another call, and then it sort of expanded to the next level, and then the next level gonna expand again to that, and then it's like something inside of that frame has expanded to the next one. It's like that.
Okay. That's a good visual. I like that.
Yeah.
So I think that seems particularly relevant here in what we're trying to do because we haven't lost, well, we still have the first value of current and parent preserved, and then we get the next value of current and parent.
Yeah, exactly. So we can fill these guys out. So inside the nested frame, the current is going to be pointing to Jeff, but the parent actually has a value now.
Yeah.
The parent is actually pointing to Jenny, funny enough, like that. And then in here, current is pointing to Jem, and then And then, whoops, Aaron is going to be pointing to Jeff in that frame. And this will happen sequentially. So it's not like they're all here at the same time. It will more be like when you're executing in the frame of Jenny, then when they get to a certain point, pop out a new frame for Jeff. And then when Jeff gets to a certain point, pop comes a new frame for Jam. And then Jam is going to finish its operations. And then Jam's frame will get destroyed and we come back to Jeff. And Jeff will need to do the rest of its thing. And then it will need to pop a new frame for Jefferson and so forth. And then when Jefferson is done, it pops back into Jeff. And when Jeff is done, it pops back to Jenny. And it'll be like sequentially like that. It's not like everything at once. Yeah.
Cool. So I think then it drawing it out and you like talking through like that really is helpful to kind of thinking through what we need to do here. So it's like we need to check to see if I can't remember what we called it, node like left, let's say if node left has value.
Okay, yeah. So if a node that left is not null, let's say.
Sure. Then we want to call traverse print with node left.
Right.
And then if we want to keep doing that, we want to keep until we get to a node left that is null.
So here is where your normal your like normal sort of loop based programming mindset needs to kind of be challenged, that kind of thinking. So that iteration doesn't need to happen in this code. And the reason is, oh, I misspelled. The reason is when you call traverse print, this call will already take care of traversal for all the children of the subnode node.left.
Okay.
Recursion is this weird thing. When you're like initially getting practice with recursion, the way I feel, the way I had to tell myself, like the thing I had to tell myself is when I make a recursive call, I just have to trust it on faith that this will do everything that is supposed to do correctly. Oh, I forgot to put in a parent. And if it did everything it's supposed to do correctly, means this will actually correctly recursively print all the elements, including the descendant of my left node.
Okay.
Which means there's no need for me to loop. Because by the same logic, all I have to do is call traverse print on the root of my tree, and I would expect it to print every element in that tree, right? So by the same logic, if I just call traverse print on my left child, I would expect my left child and all its descendants to be printed.
Okay.
Which is why I only have to call this without additional iteration or looping.
So the two lines of code, or the three that we have now, the print line 1, print node value, and then we're doing the check to see if our left node is not null, then
Right.
we call recursively. Like that's really all we need to get down but we still have to handle the right side.
You still have to handle the right side, correct?
Children, but like that, those 3 lines, the recursive, the way the recursive call works, that will take us all the way down the left side.
Yeah.
That makes sense to me.
Yeah, because so let's just imagine what happens. So we'll start with nothing again. Okay, so we start at here, and then we say, hey, print, note that value. So what we end up doing is we're gonna print Jenny, and then we're gonna call, if note that left is exists. I'm gonna say exists. If note that left exists, then we're gonna do this call, this recursive call. We should probably come up with a parent for that parameter. This would just be the node, right? Is the parent of left that node that left. So we would recursively call traverse print, and then we're back at the top, but it's at the nested level, and then line 1 is just print that value. So we're gonna print Jeff, right?
Yep.
We're gonna print Jeff, and then at the Jeff frame again, we're gonna say if node that left exists, and then print traverse print node that left, and that's gonna get us to jam.
You don't have to keep drawing the squares unless you just want to. I do feel like I have it.
Okay. So yeah, so we're gonna print jam, and then here jam doesn't have a left, so we're not gonna do this anymore. And then we're gonna actually finish this frame because we reached the end of the function for jam.
So then it goes back to where it was.
Yeah, we pop back to Jeff's frame, and Jeff's frame was sort of suspended in here, waiting for Jam's frame to finish. So it would be like we completed the function call to traverse print for Jam, and then after that, there's no more statements. So we also complete the frame for Jeff. And then again, we're back to Jenny's frame, and then again at Jenny's frame, where we also suspended on this line. And then now we come back from this line, and then Jenny's frame is also completed because we reached the end of her frame. So we destroy all the frames, and then we're gonna return back to the original calling line, which is this. And we end up just printing 3 names. But we haven't done the right side.
Right. So
it's
now
complete the right side.
The right side, yeah. So I want to say that when we exited out of the frame for Jam, and then we were back in the suspended Jeff frame, that we want to have some logic in there that says, like an else if maybe, that says else if node right, and then call traverse print again with node right.
Should have been else if though, because like you're assuming it either has a left or a right. If you do an else if, right?
And is it not safe to assume it has a left or a right? Well, it might have right.
Yeah, it might have both.
So maybe it's just a second if.
Yeah, it's just a second if. Yeah.
Okay. So we want to say if node right exists, and then call traverse print with node right and node as the parent.
Yeah, exactly. So so if we do this, then after jam's frame, so jam, we're gonna fast forward the same. So like if we're at jam's frame, we're gonna print jam,
Yep.
and then I guess just take my word for it that everything that happened so far is the same.
Yes. Yeah.
So yeah, and then we're gonna see that jam doesn't have a left node, so it skips this, and it
Yep.
also doesn't have a right node, so it skips this one as well. So we're gonna be done with jam's frame, and we come back to Jeff, and now Jeff was suspended in this line, and now it's been returned to Jeff. So Jeff is gonna continue on this line and see that, oh, I do have a right side. So now it's gonna instantiate a new frame for Jefferson. And then Jefferson is gonna print itself. And then Jefferson's gonna see it has no children, so it's gonna be done very quickly.
Yep.
And then Jeff is gonna it's returning to Jeff after this call, and then Jeff is gonna be done after that. So Jeff is gonna pop off. And then we're back to Jenny's frame, and Jenny was actually suspended here. So so when if you're doing this kind of stuff by hand, which I do make my students do sometimes, like be the computer, right? Because otherwise you have to know how the computer is going to behave precisely. Like you should be able to replicate it yourself using pencil and paper. But if you were to do that, you actually have to keep track of like what line was Jenny's frame suspended on when it created the Jeff frame. Because after Jeff is done, you have to know what line to sort of restart from in the Jenny frame. So I would like usually I would do a little arrow here in the Jenny frame, or write down the line number for the Jenny frame. If I draw the frames as, so like if I draw like, oh, this one frame, this is Jenny, and then another frame, this is Jeff, and I'll write like the line number, like we called from line 5 or something. That's how we opened up this frame. So when this frame is destroyed, we know to go back to line 5, which might be this line, and then in the Jenny frame we start from line 5 again.
From line 5. That makes sense.
Yeah. So anyway, we're back on this line in the Jenny frame, and we're just done with this function, and then now I continue, and then we're gonna have to go on to Jenny's right side.
Yes.
So it'll be like that, and then we'll get to print John here, etc. And I won't belabor it, but everything will be similar on that side, and that's how we traverse this tree.
Yeah.
Let me think. One thing. Oh, there's a couple of things that we can simplify with this code.
Okay.
One is we actually never made use of the parent variable. It's not necessary.
We don't really need it. Yeah.
Yeah, we actually don't need it. So there's no need to maintain in this case. There are some cases where you might need it, but this case we don't. And another thing is so we also can get rid of it here. Another thing is you actually could move this null check to the top instead of having two null checks here.
Okay.
You could say if node exists, or if No, does not exist. We're gonna do an early return.
Okay.
And then that way you don't actually have to do these two checks. So what will happen? And uh, this is usually like this way usually yields more condensed code because you have just one check. And this is the terminating condition, by the way.
Okay.
So you just have one terminating condition check instead of have two separate ones lying
Yeah.
somewhere in the code, and it's a little bit more easy to think about or maintain later on. So this does mean that you're gonna end up with like you create a frame for jam, and jam is like just traverse to my left, and its left is nothing. And you'll have a frame for the case of nothing. And then at the beginning of this frame, it'll just say, oh, it's nothing. So I'm just going to return. And then I destroy the frame right away.
Okay. Yeah, that makes
So
sense.
it kind of seems like it's more work. It's actually more work for the computer because, but it's less work for the human because there's less code to read here. But for the computer, it has to make this extra frame, which is actually somewhat expensive.
So why wouldn't we, if that's the case, why wouldn't we opt to have a couple more lines of code to optimize?
Just because this code just looks more condensed, and
Okay.
and it seems like, hmm, well, okay, like optimization is there's different schools of thought surrounding optimization, like making sure your code is as fast as it can be. Um, and there, this so so there are programming languages that can actually automatically optimize this is one thing,
Okay.
so that it will be fast anyway. But
Gotcha.
that's not guaranteed. Like I don't know if it's not guaranteed that statement. So you might have to verify. And I don't know if it works in JavaScript or not. I have a feeling no. Although it's hard to say because the JavaScript compilers are super fancy and they're getting better all the time. But another thing is there's a school of thought that you shouldn't worry about optimizing your code for performance at the outset, um, because other concerns are also important, like code readability.
Sure.
So when you have a need to optimize for there's a famous saying called like premature optimization is the root of all evil, which is a perhaps a little strong,
Sure.
but
Root of all evil.
yeah, it's slightly strong, and I think overly strong. But I think with any kind of debate where there are good points that can be made on both sides.
Hmm.
Both sides try to sort of fight really hard uh, to win the argument, and I think this quote is just an example of that. So
Okay.
so I think both sides has good points, and I'm not gonna take either side in this case. But I do for teaching. I do like just having very condensed code.
Okay. Sure.
All right. So, okay. So now maybe we can finally get to the ordering problem. So how do
Yeah.
we? So here have we printed things in order? No,
No.
we should print Jam first, and then Jeff, and then Jefferson, and then Jenny. So that's the output that we want. So can you think of a way to like Just look at this code. It's so nice. There's only like 5 lines of code in this
It
function.
is, yes.
It's not like our previous function was nice too. It's not bad. There's like 10
Yeah.
lines of code here. But now it's just 5 lines. So like, how would you change these 5 lines to get this tree to print in order?
Okay, so if when you say change these 5 lines, do you mean I'm not adding anything else?
Well, I'm not gonna put words in your mouth.
Okay. Okay. Well, here, let me say it this way. So my first thought after we've written this traverse print recursive function, my first thought is, well, I think we have to start from the top and work our way down. Like that's just how traversing this tree works. So my thought is, instead of just immediately printing the names or the values, there might not be names, the values, why don't we organize them? Why don't we sort them? And then in the end, print the sorted list. But I also think I might be taking the wrong approach. Like, sure, we could do that, but maybe there's a better way to do it. So
Yeah,
what I sort of
there's
what I
a
sort of want to
simpler
do.
way.
There's a simpler way. Okay. So I want to sort of table that thought for a minute and just kind of look at these lines of code and see. Node left, node right. So we're printing the value. So we're each iteration through, each time we call this, we're printing, if the value exists, we're printing it. And then we're calling the function recursively, first on node left and then on node right. Maybe we don't print first. Let's see, if we didn't print first, if we first, because we want to start all the way down at the bottom. We want to traverse all the way to our bottom and then start printing.
Yeah.
That's what we want to do. So I think we want to move our print statement in between our 2 calls.
Yeah. So just do maybe I'll make a new copy of this.
Sure. And I'm not like fully convinced that I've got this, but I'm just kind of thinking out loud here, to be honest.
No, that's the best way to do it. Tree traversal. I'm gonna call this in order.
Okay.
This is actually what it's called in the literature.
Recursive tree traversal in order. So creative.
Yeah. Okay. I'm gonna. So perhaps I will name this in order as well. Oh, by the way, the name for the first one is called pre-order, which sounds like you're trying to buy some very popular item, but but that's not what it means. It means you're gonna print yourself first before traversing your children. That's what pre-order means.
Okay.
And then now we're gonna do in order, and you're saying, why don't we just move this print statement in between these 2 recursive calls? So let's see what would happen.
Yeah.
If we did that. So now I'll just zoom out a little bit, I guess. All right. So initially we would be looking at Jenny.
Yeah.
And then I'm gonna, okay. And then we're gonna, well, it does exist, so continue. So we're gonna make a new frame for Jeff. And then Jeff does exist, so we continue, and then we're gonna make a new frame for Jam.
Yep.
and then jam does exist, and then we're gonna make a new frame regardless for
Yep.
its left child, which is nothing.
Yep.
And then we're in this frame and the node does not exist. So we're gonna be done with that frame, and then we're back to jam. And then when
On
we're
this
back,
line.
yeah, exactly. We're on this line. We've done with this line, and then now we're gonna print jam.
Yep.
And then now we're done with the print statement, and then we're gonna traverse to the right of jam over here. That's nothing, so we're gonna exit that frame right away. And then now we return to this line in the jams frame, and then we're gonna be done with jam, and then we're gonna go back to Jeff, and then Jeff was suspended on this line, so now we're done with this line, and then we're gonna print Jeff.
Mm-hmm.
And then after that, we're gonna traverse to the right of Jeff.
Yep.
And then now we're in Jefferson. Jefferson does exist. We're gonna go to the left of Jefferson, but then that frame gonna go away right away. And then now we're gonna print Jefferson. And then now we're gonna do another frame for the right of Jefferson, and then that frame goes away. And then Jefferson is done. That frame goes away, and we're back to Jeff, and it was on this line, and it's done now. So Jeff is done as well. We get rid of Jeff's frame, and we're back to Jenny. Jenny was suspended on this line to do Jeff, and then now we actually get to print Jenny.
Yeah.
And then we're gonna go to the right side of Jenny.
Wrong John.
And then John exists, so we keep going, and then we're gonna Joan exists, and then we're gonna do the left side of Joan. There's nothing there, and then we're gonna print Joan. And then after printing Joan, we're gonna go to its right side. There's nothing there, and then now we're back to Joan, and then Joan is done. Come back to John, and John was on this line, on it doing its left side. And then it's done with that, and now we're gonna print John. And then now we're gonna do the right side of John, which is Kenny. Kenny exists. We're gonna go to the left side, but there's nothing there, so we're just gonna make the frame really quickly and delete it. And then we're over here. We're gonna print Kenny. And then again, we're just gonna do that. Go to the right side of Kenny. There's nothing there, and we're done with Kenny. We come back to John's frame on this line, and then after that, he's done. And then we come back to Jenny's frame on the last line, and then Jenny is also done. And we're finished.
So cool. Yeah, just that one tiny little change. It's very elegant. This whole thing of the tree and everything being in order from left to right blows my mind. And I want to know what the inspiration. Do we see this pattern in nature? I don't know. Like, where did someone come up with this?
We do see this pattern in nature. Just look at how many not only the actual trees that you see in nature, but that's definitely true. Like if you look at the leaves of some trees, you see that there are smaller patterns in the leaf that are sort of smaller versions of the whole leaf itself.
Yeah.
So those are called fractals, where
yeah, that's what I was thinking of.
like the cauliflower, for example, is a classic fractal where it's sort of like there's smaller and smaller versions of itself. Fractals are fascinating too. I could get into that, but let's not for now.
Fair enough. It's a wrap up.
Yeah, fractals are super amazing.
Yeah.
Look at the Mandelbrot set.
Okay.
If you're in the mood for getting your mind blown, I did a couple of videos on that as well. I actually did some stuff on the Mandelbrot set, which is pretty cool. Okay, getting back to this. So, now with this, obviously, it's very simple to change this to do it in the reverse order. You just flip. You do the right first, and then
Yes.
the left after. So you also know how to print the tree in reverse. I don't think there's a technical name for the reverse order. Maybe they thought that was too trivial to give it a name. But there is a third type of tree traversal other than the pre-order and the in-order.
Okay.
So I guess if let me actually, we never completed the pre-order. So let me do that again. So the pre-order would be like Jenny, and then Jeff, I think, and then Jam, and then Jefferson,
Mm-hmm.
and then yeah, John, and then John,
Okay.
and then Kenny. This would be, so this one is in order, and this one is pre-order. Interestingly, though, both of these are different order from my queue-based one.
Yeah, I noticed that earlier. Yeah.
So this, I think, is called a breath first, I believe, because
Breath. Interesting.
breath meaning it's like it's doing level by level.
Yeah.
So the word breath first, it's coming from the terminology of searching things, which is in graph theory. So breath first search. When you're searching a graph, like for example in a social network, I'm trying to start from you, go to all your friends, go to each of their friends, etc., to see if you're connected to Kevin Bacon, right?
Yeah.
And when you're doing that, you can either do a depth first search or a breadth first search. Depth.
Oh, okay. Breadth, like breadth, depth, and breadth. Okay.
Did I spell this wrong?
I don't
There's
know
a
that you
D?
spelled it wrong, but I was thinking breath like breathing.
Oh, okay.
Like yes. So I was not on the right page. Breadth. Okay. Gotcha.
Breadth.
Like a term of measure, or what is that? Anyway, I'm with you.
Yeah, you're with me. Okay, so what I'm saying is this is breadth first search, which means you're not gonna do any of your friends until you've looked at every one of your immediate friends. And that's
Gotcha.
what this queue-based approach would do, which is different from either of these recursive approaches would generate. Um, and there's one more one. It's called post order.
Okay.
The post order is, I don't even know why you would use this, so I'll just include it for completeness. It's just like you print yourself after you've done your children already.
Okay.
So that would just mean, I think you're gonna have print Jam first, and then Jefferson, and then you would print Jeff, and then you would print Joan, and then you would print Kenny, and then you put print John, and then finally you would print Jenny.
Interesting.
That's a weird way to do it. And I can think of a reason why you might do this. Maybe you want to calculate something like how, like some statistic about about each subtree. Like you want to know how many descendants each guy has, for example,
Hmm.
or maybe maybe each node has a score or something that is assigned in some way. Like if
Yeah.
this was a social network, which it isn't, but if it were, like every person has some popularity score or something,
Yeah.
and then maybe you want to know, like, I want to calculate the sum of the popularity scores of their friends, etc. Oh, it wouldn't work in this case because you would end up having cycles. Like Joan would end up connecting back to Jenny, so Joan would also be a child of Jenny if they're mutual friend relationships. So maybe that's not a good analogy, but maybe it's more like organization, an org chart in a company.
Okay.
So this is the CEO, and these are his managers, and then we have team members, etc. And then maybe each person has a score, and then you want to sum up, the sum of the scores at each level of the tree. Then you would want to get down to the leaves first to get their scores and propagate it up to this, the next level, where it can be summed, and then propagate it even more up to the top.
Yeah. Would it be used in doesn't React use tree structures, or like not even
Yeah.
React, the DOM, like just the DOM, like
Yes.
the DOM using tree structures? And I'm just thinking the language you're using is like events bubbling up to the top, the
Yes.
parents to parents.
Oh
Maybe
yeah.
it's used in that kind of context.
Well, I mean, yes, definitely. The DOM is a tree, and there's actually two ways in which the events can bubble. I think one is called capture phase, and the other one is called oh, I don't remember the other one. But
No worries.
the capture phase is like, yeah, so like if this were a DOM tree, so 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 maybe like this is a div.
Hmm.
This is a paragraph. There's a header. This is span. Wait, is I don't know if maybe okay. I don't think a header is supposed to be in a paragraph. No,
Probably
no,
not.
no. Okay.
I don't know. But
Let's
it's
say
okay.
it's an A, and
Perfect.
then a span, and then there's an image. So let's say if somebody clicks on this image, right?
Hmm.
We have a click.
Yes.
Uh, so what the browser has to do, click. The way the browser figures out that you clicked on an image is if well, it has this tree structure, but in addition to this tree structure, it also needs to have the image coordinates and the rectangle for each element. So like it needs to know that in image terms. Maybe I am running out of room, but hold on. Move this away a little bit. So in image terms, we have a diff. Oh, actually, the top thing is the diff. This
Okay.
is already the diff, and then we have paragraph 1, and we have paragraph 2, and then we're gonna have a link. The link is gonna look like link http blah.org, and then we're gonna have hello world, some text. So this is the A. And then in the next one, we have another span. Hello. And then we actually have an image here. Oh, maybe not an actual image, but we have an image. Okay. This is an image. So we click on this, and the browser has to figure out, well, your position of your mouse, the position of your mouse is within the rectangle of this, the rectangle of the image element.
Mm-hmm.
But it's also within the rectangle of this paragraph element. But it's also within the rectangle of the div element. So the question is, how does it check? Does it need to check it for all three of them? Yes, it does. And in which order does it check? So, well, since this is a tree, it would make sense that it starts at the root of the tree. So,
Right.
so the browser actually doesn't magically know that it lands inside the image element. The browser actually starts. Okay, there might be ways it can manage to know that, but that's not the simplest way. That might be like the browser is trying to really go out of its way to be super fast. There might be ways to do it like that, but let's say we're not doing that. But so
Okay.
we're gonna first check. Like we got a click in this coordinate,
Yes.
5670 or something like that, and then we're gonna just check from the top of the tree. Is it in the rectangle of the div? Well, it is. So if it is in the rectangle of the div, we keep going. If it's not in the rectangle of the div, that means you click outside of the div. There's no need to check any further. We know we didn't click in any of the elements in the div.
Okay.
Although that might also not be true when you have like fixed or absolute positioning.
True.
But,
Yeah.
but let's not worry about that for now. Let's
Sure.
say
Normal flow.
let's say our browser is doesn't support that kind of weird stuff. um, but so then it's like, okay, yeah, we click on the div. Now I can immediately fire a click event on the div element, and right away, and then I'm going to check the children. So we're gonna first check if click on this. Yeah, if I did click on it, so I'm gonna continue to find the most specific things in my descendants that it clicked on. So first I'm gonna check the first P. The first P, well, is this upper rectangle. No, we didn't click in the first P. So there's no need to descend into each children. So we just try the second P. We did click on the second P. So I'm gonna descend into each children and go to this span that says hello. No, we didn't click on that span. So we come back up, and then we go to the image, and then we say, yeah, we did click on this image, and therefore we click on the image. Here's the question. At what point in time do you fire that on click event? And are we gonna fire the on click event on the div and the paragraph and the image? Well, probably yes, because if the programmer register on click event on any of these elements along the path, we probably want to notify them, right?
Okay.
But then the question is, in what order should you fire them? Should you, like, if the user register on click handler for the paragraph and the image and the div, in what order should those three handlers be called? Should it call the one for the image first, or the paragraph first, or the div first? Oh, there's no real right answer, and we should probably just allow both ways to work. And in the browser, there is both ways.
Okay.
It can work both ways. When you add a listener, you can choose to add it either to be triggered while it's traversing the tree on the way down, or while it's coming back up. you, so then you can get either order that you want.
Cool.